Hello, everyone, and welcome. So today we are going to tackle one of the most powerful ideas in all of probability. And trust me, once you understand this, it's going to completely change how you look at problems. It's a proper game changer. Now, just think about this. Usually in class, the questions are like, if a product is from machine A, what's the chance it's defective? Simple enough, right? But what if we flip the question completely? What if we already have the defective product in our hand? We have the result, we have the evidence. How do we work backwards to find the probability of the cause? Well, today we are going to learn the mathematical way to solve exactly these kinds of reverse probability problems. Okay, let's dive right in. So we're very used to calculating the probability of an effect when we are given a cause. For example, what's the probability of getting heads if we toss a coin? But Bayes' theorem, it's like a detective's special tool. It lets us do the complete opposite. We see the effect, the clue, and we work backwards to figure out the probability of the cause that led to it. To make this concept super simple, let's just frame our entire lesson today around one fun idea. We are all going to be probability detectives. Yes, that's right. Imagine we are at a crime scene. We have a clue. This is our evidence or the effect. Our job is to look at our list of suspects, the causes, and then figure out mathematically which one is the most likely culprit. Sounds fun? No? Now, what does every good detective do before they even start solving a case? They organize their information. You cannot just jump in randomly. You have to lay out all your clues and all your suspects in a proper, structured way. Believe me, this is the most important step of all. So the first technical thing we need to understand is something called a partition of a sample space. I know, it sounds complicated, but I promise it's very easy. Just imagine there's a new viral trend on Instagram. The partition is just our list of suspects who could have started it. Maybe influencer A, or influencer B, or influencer C. Mutually exclusive simply means it can't be both A and B who started it. And exhaustive means it has to be one of them from our list. That's it. The partition is just our complete and non-overlapping list of suspects. Look, this slide translates the math terms perfectly into our detective analogy. Our suspects, influencer A, B, C, these are called hypotheses in probability. Our initial guess about them, like how often do they start trends in general, that is the prior probability. And the likelihood that they would start our specific clue, let's say a dance trend, that is the conditional probability. This table is basically how we organize our case file. Okay, detectives, next step. Before we can point the finger at any one suspect, we need to calculate the total probability that our evidence, the dance trend, would even exist in the first place, considering every single one of our suspects. This is called the theorem of total probability, and it's just 4 simple steps. For each suspect, you multiply their initial probability by their chance of creating our evidence. You do this for every single suspect on the list, and then you just add all those results together. This gives us the total probability of the evidence, what we call P of evidence. It is that straightforward. All right, the moment we've all been waiting for. It is time to reveal the master tool, the secret formula that every probability detective uses to crack the case and find the true cause. This right here, this is the question we want to answer. What is the probability of a specific suspect, given that we have already found the evidence? How on earth do we calculate this reverse probability? And here is the answer. This is Bayes' theorem. Now, don't be scared by how it looks. Look closely at it. The entire denominator, what is it? It's just the sum of all possibilities. That is the total probability we just learned how to calculate. And the numerator, it's just the single piece of that sum that belongs to the specific suspect we are investigating. So the most important thing to remember is the logic. The formula is simply the probability of our suspect causing the evidence divided by the total probability of the evidence happening at all. That's it. Okay, enough of all this theory. The best way to learn is by actually doing. So let's put our detective skills to the test with a real problem straight from your NCERT textbook. We will solve a case right now, together. So here is our case file. We have 3 machines, A, B, and C. These are our suspects. We know the percentage of bolts they each produce, and we also know their individual defect rates. Now, we find a defective bolt. That is our evidence. The question is, what's the probability that our specific suspect, machine B, is the culprit here? First step, always, organize the clues. Let's put everything neatly in a table. Our suspects are the machines. The prior probability is just their share of manufacturing, which we'll write as decimals. The evidence likelihood is the probability that that specific machine would produce our evidence, which is, a defective bolt. I'm telling you, getting this table right is half the battle won.
Now we just apply what we've learned. We need to find the denominator for our main formula. Remember, this is the total probability of finding a defective bolt, doesn't matter which machine made it. This is our P of evidence.
And we calculate it exactly as we learned. For each machine, we multiply its production share by its defect rate. So for machine A, it's 0.25 times 0.05. That gives us 0.0125. For machine B, it's 0.35 times 0.04, which is 0.0140. And for C, it is 0.40 times 0.02, which is 0.0080. We add them all up, and our total probability of finding any defective bolt is 0.0345. Okay, we're at the final step. It is time to apply the detective's formula. We want the probability that the bolt came from machine B, given that it is defective. So our numerator will be the specific calculation just for machine B, and the denominator will be the total probability we just found. Now we just substitute the values. The value for machine B's contribution was 0.0140. The total probability was 0.0345. We just divide them. To make the calculation simpler, we can write it as 140 divided by 345, which simplifies to 28 by 69. And case closed. See, it's just simple calculation once you have set up the problem correctly. You are doing great. So what have we really learned today? You haven't just learned some mathematical formula. You've actually learned a whole new way of thinking. You've gained a mental superpower for updating your beliefs based on new evidence. Let's just quickly recap the main points. Remember, Bayes' theorem is for working backwards, from effect to cause. You must always start by organizing your information. Identify all possible causes, their initial probabilities, and the likelihood of the evidence. Then it's a simple two-part logic. Calculate the total probability of the evidence, and then divide the part for your specific suspect by that total. But the biggest idea is this. It's a tool for updating what you believe when you get new information. And that brings us to the end. I just want to leave you with this one thought. Now that you have this powerful tool, now that you can think like a probability detective, what common idea or belief that you hear every day will you test first? Think about it. The power to reason with evidence is now in your hands.